So, welcome everyone. This is my intro to material science presentation. I will be speaking about biodegradable polymers, especially emphasizing on polylactic acids. So, my name is Elamthal Abuobaida, and let's start off by introducing what does it mean, what does PLA mean, or what does polylactic acid means. It is a biodegradable material that's helping to address the global plastic pollution crisis. Now, unlike traditional plastics, which can persist for hundreds of years, PLA can break down naturally, helping to reduce environmental impacts and carbon emissions. Polylactic acids, or formerly known as PLA, is made from renewable resources like cornstarch or sugarcane. Through fermentation and polymerization processes, these natural sources are converted into lactic acid, which is then built into long polymer chains. Now, PLA is combustible under industrial conditions and is widely used today in packaging, 3D printing, and even in biomedical applications. Okay, so this is a 3D molecular model of the PLA that I created using Gaussian view. What you're looking at is a oligomer, which is a small chain with three different repeating units that I will highlight. Let's see. These are these molecules. And those are just repeated three times to create this PLA 3 ND one. These three repeating units are consistent of lactic acids that are linked together. The backbone is built from a ester linkage, which is connecting different um, carbon and oxygen atoms together uh, between each one. Modeling a few repeating units like this helps with visualizing the basic building blocks of a PLA structure. In actual materials, these chains can be hundreds or even thousands of units long. And small changes is how these chains are arranged together, and those can greatly impact the mechanical strength, flexibility, and how quickly the material degrades and how it behaves as far as chemical properties. The way these polymer chains organize themselves determines how the material behaves. So in crystalline regions, the chains are tightly packed, making the material stronger and more heat resistant, but slower to degrade. On the other hand, in amorphous regions, the chains are disordered, making the material more flexible and faster to break down. And lastly, the structure-property relationship is fundamental for tuning PLA for different applications, from rigid packaging to flexible films. Scientists study PLA behavior through a range of material characterization techniques. Tensile testing measures how much stress the material can handle before it breaks. That is very much important for structural applications. We also have thermal analysis, which is like differential scanning calorimetry, which measures how PLA reacts to heat, helping determine properties like melting point and glass transition temperature. These methods help ensure that PLA products perform reliably in the real world conditions. Thanks to its combination of biodegradability and versatility, PLA is used in many industries as of today. It's a common, it's very common in eco-friendly packaging, as well as 3D printing filaments and medical devices like sutures and implants. In the medical field, PLA's ability to safely break down into lactic acid inside the body makes it very much practically valuable. Polylactic acid shows how material science is driving sustainable innovation. By understanding how molecular structure connects to material properties, we can design a very much smarter material that supports a cleaner and a greener future. But with that being said, thank you guys so much for watching, and I hope you gain valuable insights about PLA structures, uh, polylactic acids, and how they could be biodegradable for a greener and better future.